The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Main fundamental frequency here, nu. All right? Now, I should tell you that the model that we used to get these vibrational energies for a molecule is actually called the harmonic oscillator model. It is a model, right? It is a model, and it predicts that the spacings between these energies are all equal. The reality is that the spacings aren't all equal. The reality is that this molecule is an anharmonic oscillator, and that although way down here in the well the spacings are just about equal, v equals 0, v equal 1, v equal 2, but as you get further up in the well they do start to come together, right? And they actually converge to the dissociation limit. You don't have to know that right now. You'll see that in later courses, but I just wanted to make you aware of that. All right, that the harmonic oscillator model works pretty well down here, right? But the harmonic oscillator potential function actually looks like that. A real potential function looks like that. This becomes anharmonic. All right, so those spacings do get closer together. But that's for the future. Now, you can also put enough vibrational energy into the molecule to break a bond, right? When you get up to here, right, you can put enough vibrational energy in this hydrogen and the chlorine. Hey, they'll, as they oscillate out, hey, they'll just keep going if you put enough energy. You get up here, when they stretch, they'll just keep on their merry way. They won't come back. They won't be a restoring force. So by putting a lot of vibrational energy into the molecule, you can break your bond. And in fact, that is what happens when you break a bond. You've got a lot of energy in that bond, vibrational energy, and the molecule, the two atoms just keep flying apart. Okay? Okay. So that was our diatomic molecule. And what I now want to just talk briefly about are polyatomic molecules. Because we said in a polyatomic molecule, such as water, we have several different vibrational modes. And each of those vibrational modes actually has a different fundamental frequency. And each of those vibrational modes can be represented with this sort of interaction potential. Okay, sometimes it's not as simple a coordinate system because, hey, you got some bends, so you got this, plot this as a function of angles. It's not easy to draw. But each one of the vibrational modes in a polyatomic molecule can, in effect, be represented by some kind of energy of interaction like we drew here for this diatomic molecule. It's just a little bit more complicated because your coordinate system's a little more complicated, particularly when you start talking about bends, right? Okay, but let's take a look here on this on the side walls. What I'm showing you is a vibrational spectrum of water. And again, this is just the, we've got some infrared radiation that is being directed at a sample of water molecules. And we're measuring the intensity of that radiation at a photodetector as a function of the frequency of the radiation going through our sample. And when the molecule absorbs radiation at that frequency, well, then that intensity at the detector goes down. All right? So what you see here is just a hypothetical spectrum for water. You see that the molecule is absorbing some radiation here at 1595 wave numbers. Well, that 1595 corresponds to the fundamental frequency of vibration of this bending mode, of this, hydrogen bending mode. That's 1595. That's the frequency in wave numbers with which that hydrogen bond is bending or vibrating, right? This is also the energy between the V equals 0 and V equal 1 mode. This represents excitation from V equals 0 to V equal 1. Okay. All right. And then way up here you see another transition at 3652. Well, that we know to be the symmetric stretch. That is, both hydrogens moving in or out at the same time. 3652 wave numbers. That's the fundamental frequency for that particular vibration. It also represents a transition from V equals 0 to V equal 1. And then finally at 3756, well, that's the anti-symmetric stretch, where one of the hydrogens is moving out and one of the hydrogens is moving in, right? Anti-symmetric stretch. It also is the V equals 0 to V equal 1 transition. So that's what you would measure in an infrared spectrum, actually infrared plus Raman, but we'll leave that out, spectrum of water, okay? And what's interesting is that any molecule that has an OH stretch in it, or any molecule that has an OH group in it, if you take an infrared spectrum of it, what you're going to see is that it has a transition somewhere in between 3,400 wave numbers and about 3,800 wave numbers. So if you had an unknown compound and you put it in your infrared spectrometer and you saw a transition somewhere in between 34 and 38, hey, immediately that's going to clue you in that you have an OH stretch, because no other molecules that are at all common are going to have a fundamental frequency in that range. So you can see how this infrared spectroscopy can be used as an analytical tool to figure out what molecule you have. And of course, the actual frequencies then are a fingerprint of the molecule, all right? But just in general, if you didn't know anything about the molecule and you saw a stretch in this range, hey, you know you got an OH bond there that is undergoing a symmetric here or an anti-symmetric stretch if you've got two OH bonds, all right? Likewise, say you had a carbon-hydrogen stretch, carbon-hydrogen bond. Well, what you would find is that all carbon-hydrogen bonds have fundamental frequencies from about 2,800 wave numbers to 3,100 wave numbers. If you see a transition in that range, you know you've got a hydrogen bonded to a carbon, all right? Because again, there really isn't anything else that's common that has a vibrational frequency in that range. When you get to a little lower frequencies, well, then it's a little more difficult because there are lots of different other modes that have vibrations which are a little bit lower frequency. But again, the specific number will identify the molecule for you. One other thing is that just in general, bending modes here, right, have lower frequencies than stretch modes. That's a general statement, which is true. Also, generally, symmetric stretches have lower frequencies than anti-symmetric stretches. That's true. Okay? All right, and you'll see more of this infrared spectroscopy used as an analytical tool, essentially, when you take some organic chemistry. All right. Well, what I want to talk about now is the other degree of freedom internal degree of freedom in molecules, and that's molecular rotations. Well, molecular rotations are quantized just like molecular vibrations are. So let me take my HCl again and draw this intermolecular interaction potential. And let me put my V equals 0 level down here. Okay. And then just for ease of my diagram, I'm going to put my V equal 1 level up here. Okay. All right, so rotational levels, hey, they're quantized. And the rotational quantum number is given the symbol J. So for example, if you have a molecule in the first rotational state, that first rotational state then will be right here. We'll call that J equal 1. And then if you have it in the second excited rotational state, well, that's going to be right there. We'll call it J equal 2. And the third rotational state, well, that's going to be right there. We'll call it J equal 3. And the fourth, J equal 4. Okay? Now, if you have a molecule in the ground rotational state, well, that ground rotational state here is J equals 0. And it is sitting here right on top of the V equals 0 level for the ground rotational state. All right? So the bottom line is you can have a molecule in the ground vibrational state and the ground rotational state. If that's the case, this is how much energy it has. When you're in the ground rotational state, that's 0 energy, as we're going to see in a moment. You can have a molecule in the ground vibrational state in the first excited rotational state. If that's the case, that's the energy. You can have a molecule in the ground vibrational state and the second excited rotational state, then it has that energy. You can have a molecule in the ground vibrational state and the third excited rotational state, it has that energy. All right? But you can also have a molecule in the first excited vibrational state right here and in the J equals 0 state. Well, if that's the case, it has that energy. You can also have a molecule in the first excited vibrational state and the first excited rotational state. Well, then it has that energy. Or a molecule in the first excited vibrational state and the second rotational state. Well, then it has that energy. All right? So each one of these vibrational states has on top of it a manifold of rotational states. Okay, the rotations and vibrations for our purpose here are not coupled. All right, you can have so much in vibration, so much in rotation. I want you to also notice that the difference in energies between rotational states is much smaller than the difference in energies between vibrational states. All right, that is a general statement that is correct. All right, so now we have a nice analytical expression again for the rotational energies, the loud rotational energies of molecules. And that analytical expression is the following. It's E sub j is equal to h squared times j plus 1 over 8 pi squared times I. I is the moment of inertia. I'll explain that in just a moment. Okay? So what does this say? Well, this says that when j is equal to 0, the rotational energy here is equal to 0, because at j 0, hey, this makes this all go away. So the molecule has no rotational energy in j equals 0. When j is equal to 1, hey, we put in j equal 1, we calculate that. Comes out to be h squared over 4 pi squared times the moment of inertia. All right, this is j equal 1. For J equal 2, the molecule has 3h squared over 4 pi squared amount of rotational energy. For J equal 3, it has 3h squared over 2 pi squared times the moment of inertia. All right? So the energies go up. Okay, now, suppose I have a molecule in V equals 0, J equals 0, and it makes a transition here to J equal 1. What is the energy difference between those states? Well, J equal 1 minus energy J equals 0. That's h squared over 4 pi squared times I minus 0. That's just h squared 4 pi squared I. Okay. How do we make that transition? Well, to make this transition right here, we're going to need a photon. That photon is going to have an energy exactly equal to this. Right? So our photon, E equal h nu, well, that's got to be equal to h squared 4 pi squared times I. I can solve for the frequency of the photon that I need to make that transition. The frequency of that photon, then, is h over 4 pi squared times I. Okay, that's the frequency of the photon that I need. Now, in the case of HCl, right, we said that HCl has 2 rotational modes. It has a mode, a rotation around this axis, right? And it also has a mode, it's a rotation around this axis in the plane of the board. These 2 rotations are degenerate. So, if you put in a photon with this frequency here, it will excite either this rotation or that rotation. Okay? Either rotation. Okay, so now let's look on the side wall here. How do we do the experiment? Well, again, just like we do it in the infrared, except that the energy of the photon we now need is in the microwave range. All right? Microwave spectra measure rotational spectra of molecules. And so again, we have a microwave radiation monochromator coming out, going through the sample, photodetector. Look at the intensity of the photodetector as a function of the frequency. At some frequency here, you see a dip in that intensity. Well, that's where the molecule absorbs. Right? And in the case of HCl here, the frequency of that absorption for J equals 0 to J equal 1, well, that frequency occurs at 6.3 times 10 to the 11th hertz. All right? So that would be the frequency of the photon that you would need for absorption. Yes? I'm sorry? We got into the microwave range here because the spacings between the rotational states are much lower than the spacings between the vibrational states. And I just actually wanted to make that point here. We can calculate in terms of the energy here what this spacing is. Let's do that. All right, so if we want to know the change in energy from J equals 0 to J equal 1, right? That change in energy is just h times the frequency of the photon. That photon there, that makes that transition happen. So you can plug that in there. So we have 6.6261 times 10 to the minus 34 joule seconds times the frequency, 6.3479 times 10 to the 11th hertz. Right? When you do that, you should get 4.2062 times 10 to the minus 22 joules. or if I convert that to kilojoules per mole, the kilojoules per mole is 0.25330 kilojoules per mole. Okay? In general, the difference in the spacings here, the energy difference for vibration, we said is something between 3 to 40 kilojoules per mole. Right? That's the difference between V equals 0 and V equal 1 generally for a large range of molecules. The difference in the frequencies here for rotation, delta E, that's more like something on the order of 0.01 to about 1 kilojoule per mole. That's what is typical. All right? So rotations are much closer in space, much more closely spaced in energy. Yes?
Why is Hertz used for discussion instead of observability?
Well, in the case of the rotational spectra, there's a little bit more diversity in what units are used. And the reason is this. They're more closely spaced. And the whole wave number came into use when, in vibrational spectroscopy, when the way people would analyze the spectra would be to take a photographic plate of the light coming in, and you'd see the lines separated in space, and people would take a ruler in centimeters, right, to measure the spacings between the lines. So that's historically how the wave number unit came to be. The problem is that doesn't work so well in rotational spectroscopy often because the spacings are much closer together. And so, depending exactly what kind of diffraction grating used, it isn't totally used. The wave numbers aren't always used. Sometimes they're the frequency. We go back and forth. And in your homework problems, I go back and forth too. You really have to deal with both kinds of units. All right? Okay. All right, but now one of the usefulnesses of this rotational spectroscopy in getting, say, this frequency for the transition, one of the usefulnesses there is to calculate the bond length of the molecule, to determine the bond length of the molecule really very accurately. Because what we said over here is that that frequency for that transition is this, right? The frequency of that transition is h over 4 pi squared times I. And I is the moment of inertia. The moment of inertia is the following. Maybe you've had this in 801? No, not yet. Oh, you will. Okay. The moment of inertia is the reduced mass times the distance between the two masses. In our case, for the HCl molecule, it's the equilibrium bond length, R sub E squared. The reduced mass is what I gave you before, M1, M2 over the sum of the two masses. Again, it is a way to reduce a two-body problem to a one-body problem, where the one body is this fictitious body of reduced mass, but it is exact. There are no approximations. This is correct, okay? So that's the moment of inertia of the molecule. It's a property of the molecule depending on the mass and the bond length. So you can see if I substitute that in there, h over 4 pi squared times mu r sub e squared, and then I go and I solve for r sub e, well, r sub e is h over 4 pi squared mu times mu to the 1/2, right? In the case of HCl, if I go and I stick in, and actually I think this is all on my slide here, right? If I go and I stick in the value for nu, the equilibrium bond length here is really 1.2748 times 10 to the minus 10 meters, all right? We can really measure these frequencies really vary with high precision and high accuracy. All right? So all bond lengths really come from measurements now of rotational spectra. All bond lengths in the gas phase, wherever we can measure the rotational spectra of a molecule. All right, so that's one of the main uses for rotational spectroscopy. Okay. Questions? All right. If not, what I want to do is to leave the subject of internal motion, and I want to talk for the rest of the hour and a little bit on Friday about another topic, which is intermolecular attractions. Interactions, or I'm going to write it here as attractions. And the bottom line is I want to try to understand on a microscopic scale deviations from the inner gas law, PV equal nRT. Okay. All right. So you know PV equal nRT, that if I made a plot of the volume versus the temperature, and I kept the pressure constant, say the pressure is at 1 atmosphere, and the number of moles in my gas is a constant. Well, you know that what I should see from that equation is a straight line. But suppose I took a balloon filled with air, and I started to cool down that balloon. Well, what would happen? In that case, the pressure is constant. The atmospheric pressure is essentially constant. What would happen is that that volume would decrease. It would decrease in a linear manner with temperature. Everything would be fine until at some low temperature, this volume would start to deviate from the straight line dependence, start to go down, and then all of a sudden, hey, the volume would go very low because, of course, at roughly 77 degrees Kelvin, which is the boiling point of nitrogen, the liquid would condense. Okay, so the volume gets very small. I could also do that with helium if I took a helium balloon, right, and I cooled it down. The volume would decrease, but then as I got pretty cold, the volume would start to decrease faster than predicted by the inner gas law. And then, hey, right at 4 degrees Kelvin, the boiling point of liquid helium, well, the volume would then just kind of plummet. And so you can understand what happens right here, but we also want to understand why does the PV equal nRT, why does that start to deviate before we get to the boiling point of the liquid? And the reason is because of these intermolecular attractions. So for example, if I had in my gas, right, this nitrogen molecule headed toward the wall of my container, and it's got some initial straight trajectory. It's going to hit the wall where it's going to exert this force, which will lead to my macroscopic pressure. But if there's an oxygen molecule around, that nitrogen molecule could indeed be deflected by these attractive interactions, circle around it, and then finally hit the wall. So the nitrogen would be delayed in hitting the wall. If it's delayed, well, then my force is going to be not as great because it's momentum change over the change in time between collisions. My pressure is going to be lower. If, in fact, this nitrogen experiences some attractive interaction which delays it from hitting the wall. Okay? And therefore the pressure is lower, or vice versa. In this case, if I kept the pressure constant, right, the outside pressure constant, then the volume would go down. Now, why is that the case? Why should nitrogen and oxygen actually attract each other? Well, in order to talk about that, we have to think a little bit more carefully about what the electron distributions are around nitrogen molecules, oxygen molecules. You know, we treated in the sodium chloride, lithium fluoride, hey, we treated those things as point charges. Well, we have to be a little more sophisticated now in thinking about what the electron distributions are in these kinds of molecules, nitrogen or oxygen. And let me, for the ease of just drawing this, let me just talk about the inert gas here, argon. Well, as you may or may not know, this, on the average, the electron distribution around argon is spherical. But although quantum mechanics does not allow us to see this, this electron distribution does fluctuate. And at some momentary time, it could be that the electron distribution here is a little bit larger on one side of this argon, and then the argon nucleus here is a little bit deshielded. So we kind of have a charge shift here, positive here, minus. When we do that, this is a dipole. We've separated charge in space. That's what a definition of a dipole is. And then, of course, if there's another argon atom around, well, this dipole then is going to induce the charge distribution around another argon, so that now the positive end is going to attract or distort the electron distribution around argon in this way, right? And this will be the positive end. And so we've got a dipole, an instantaneous dipole, which has induced a dipole, an instantaneous dipole, in a neighboring argon atom. And now we've got these two dipoles together, and they are oriented in opposite directions, and that's an attractive interaction. The net result is an attraction. And of course, we call that an induced dipole interaction. We also call that sometimes the London dispersion force. Okay? So this is not a permanent dipole. This is momentary dipole. This is an instantaneous dipole, which induces then an instantaneous dipole in the neighboring molecule, or the atom. The result is, because you got these two dipoles now aligned in opposite directions, the result is a lowering of the energy. There's a net attraction. That's a reason why in this nitrogen and oxygen there might be some attraction. The nitrogen may in fact be deflected from its trajectory, right, and hang around the oxygen a little longer before it hits the wall. Therefore, the pressure is lower than you would expect, or the volume is lower than you would expect if you were keeping the pressure constant. And we can draw that interaction energy for two argons, right? So here are two argons separated. Argon limit, if we draw the energy of interaction, hey, there's some net attraction. This is 0, all right? And that net attraction here, as they come closer and closer together, is a whopping 0.996 kilojoules per mole. Not very large, but there is a net attraction. Right? You can also see that there's a value here of R at which that attraction is the maximum. And that is the equilibrium bond length of the molecule argon 2. So, can you form a molecule between two inert gases? You sure can. Right? We call that, sometimes we call this a van der Waals dimer. Right? You can make these molecules. There's the bond length. In the case of argon, that bond length is 3.8 angstroms. Okay? But the attraction, the origin of that attraction is this induced dipole interaction. You can make two argon atoms stick to each other. Okay, but now I do want to compare this energy of interaction right here between two argons with the energy of interaction between two hydrogen atoms that are covalently bonded, right? The energy of interaction between two hydrogen atoms that are covalently bonded, well, I've run out of board space here. Well, what's that look like? Well, what that looks like, well, here's the two hydrogens separated. The bond length here is 432 kilojoules per mole. All right, look at how much stronger the H2 bond is in the case of a covalently bound molecule. 432 as compared to the 0.996 in the case of the argon. Look at what the equilibrium distance is here in the case of H2. It's 0.74 angstroms compared to 3.8 angstroms in the case of argon. Okay? So this is not a covalent bond, the induced dipole, but it is a bond. Okay, but now you might say, well, you know, that wasn't a really fair comparison because hydrogen is much smaller than argon. So, of course, the bond length in hydrogen is going to be much smaller than that in two argon atoms. And therefore, if the two hydrogens are much closer together, hey, the energy of interaction's got to be much stronger. Well, to show you that that isn't really the appropriate way to think about it, look at this diagram here on the side board, where what I'm plotting for you here is the argon-argon interaction potential. Here it is, right? It's this light kind of reddish line, argon-argon, versus the chlorine-chlorine. Here's chlorine-chlorine. Argon and chlorine are about the same mass. They're about the same size. What do you see? Well, you still see that the argon-argon interaction is much weaker. You can hardly see in this drawing here, you can hardly see the attractive part of the interaction potential on this scale. Chlorine-chlorine, on the other hand, boy, look at that, minus 200 kilojoules per mole. And chlorine-chlorine is much closer in the equilibrium bond length. What is it, 1.9, something like that? Whereas we have 3.8 over here for argon-argon. All right. So, you know, in that covalent bond between two chlorine atoms, that's a different interaction than this induced dipole, where we have overlaps of electrons, the wave functions constructively, destructively interfering. That's different than the induced dipole interaction. Now, it turns out that we actually do have a nice analytical form for the interaction potential due to these induced dipole interactions. And let's take a look at that. For these, what they're sometimes called dispersion interactions. We leave off the name London. We have a nice analytical form for these dispersion interactions. And the name of that analytical form is the Lennard-Jones potential. Lennard-Jones was way ahead of his time, a gentleman in England, late 1800s, who decided that, you know, when he got married, it wasn't really fair for his wife, whose last name was Leonard, to take his name. So they both had last names, hyphenated names, Lennard-Jones. So that's Mr. Lennard-Jones, all right? And that potential function looks like this. We're going to call it capital U, LJ, Lennard-Jones. It's going to be as a function of R. R is the distance between. I'm going to use argon as the example, the two argon atoms. That's going to be equal to 4 times epsilon. I'll explain what epsilon is. Times sigma over R to the 12th power. I'll explain what sigma is in a moment. Minus sigma over R to the 6th power. Okay? That's my potential form. Now, when I plot it, well, it's going to look like every other interaction potential that we've drawn here, because I can't on the board draw things very accurately. But this is argon plus argon way out here. This is a function of R. We're going to start out at 0. This is going to go down, and we come back up. Okay? That's the general form, and this is the actual expression for that interaction. Now, what are these parameters here? Well, this epsilon here, that epsilon is this well depth. It is measured from the bottom of the well, although the argon atoms are never at the bottom of the well, right? They have the 0-point energy. This epsilon here is this energy from the bottom to the dissociated atom limit. What's this sigma? Well, this sigma is related to the equilibrium bond length. In the Lennard-Jones potential here, the equilibrium bond length is equal to 1.12 sigma. All right? That's a parameter. To get it, you would take the derivative of the potential function, set it equal to 0, calculate the value of R. That would give you a 0 in that derivative. That's a maximum or a minimum, and it'll turn out to be a minimum in this case. All right? That's what sigma is. Now, what are these two components right here? Well, this component, this sigma over R to the 12th. Well, what this describes are the repulsions in this interaction. It's a good description of the core electron repulsion. All right? Not the repulsion due to the outermost electrons in argon, but the repulsion due to the core electrons, the n equal 1, the n equal 2 electrons. And it describes the nuclear repulsion. It is a 1 over R to the 12th dependence. If I plot that, it would look something like this. It's repulsive everywhere. It is what we call a short-range interaction. And this is important. What do we mean by short range? Well, short range means that it only has a value when R is small, right? Because it's a 1 over R raised to the 12th power. So if R is large, right, and you put a large number in the denominator and raise it to the 12th power, hey, the result is nothing. Right? The result is something close to 0. So this first term is 0, and R is very large. So that's why we call it a short-range interaction. And you can see that, right? This really starts taking on value when r is pretty small. But then there's this part, right? There's the sigma over r to the 6th term. That is the attractive interactions. If I were to plot that, it would look like that, right? That's the induced dipole interaction. We could actually write down the energy of interaction between these two induced dipoles and find out that this is a 1 over r to the 6th power. We're not going to do that, but you could do that. Okay? These are always attractive. The sum of the two, of course, gives us the actual shape of that interaction potential. All right, but this interaction here is longer range, or we call it longer range. It's longer range because it's only 1 over r to the 6th, right? And so r doesn't have to be that small in order for this term to make a contribution. So as r has a larger power here in the denominator, that's shorter range interaction. As it gets a smaller power in the denominator, hey, that's a shorter range interaction. Now, the other thing that's interesting and important here is that this value of sigma, right, this value of sigma, and I said that r sub e was 1.12 times this sigma. The value of sigma is actually the definition of what we call a van der Waals radius, right? That is, in the case of argon here, right, the equilibrium bond length here is 1.12 sigma, all right? And so r sub e, 1.12 sigma, I said, maybe I didn't say, for argon, that parameter is 3.4 angstroms. And so the bond length here is 3.8 angstroms. Okay? But the van der Waals radius, is given by this 1.12 sigma over 2. All right? The van der Waals radius is the radius, in this case 1.9 here, is the radius that you use in these space-filling models. On the side walls, that top model is a space-filling model. And you can see, you know, somehow you have to decide how large should those hydrogens be that are sticking out in space that aren't bonded to anything. And the radii that are used are these van der Waals radii, because that's the radius at which you have this attractive interaction due to the induced dipole. All right? And that's how those sizes are determined.